Now that you have a basic understanding of the scripting concepts within Unity, it's probably a good idea to take a look at some of the Zombie Toys project scripts to see how you can apply some of the knowledge that you have to things that are already in here. There's a few examples specifically that I wanted to highlight. The first such example is inside the mouse location script. The mouse location script is useful because it allows different game objects to figure out where in the world your mouse cursor is. What's interesting about this is your mouse cursor is on your screen, which is a two-dimensional space. There is no z-axis. Instead, we can use a built-in method to draw an imaginary line from the camera through the mouse cursor on the screen into the world to figure out where in the world in 3D space your mouse cursor would be. We can see on line 37, that's where we do this calculation. We generate something called a ray, which is basically an imaginary line. We do this using the screen point to ray method, which is part of the camera, which we reference through the camera type. We pass into the screen point to ray the screen position variable, which we can see on line 34 is the input.mouse position, or where the cursor is on the screen. You'll also notice lines 30 through 35 have another bit of code that's used throughout the project. These are called platform defines, and they allow us to specify which code is used based on what platform we're currently on. So lines 30 through 33 reference code that is only used if we happen to be on Android, iOS, or Windows Phone 8, generically a mobile device. Line 34 is what we're going to do if we're on a PC or Windows or pretty much anything that's not a mobile device, and we can safely assume that we have a cursor. What's worth knowing is that the input.mouse position returns back a vector 2. Now you're used to vector 3s being x, y, and z. However, the screen does not have a z coordinate space, so a vector 2 is simply an x and y. Therefore, the screen point to ray method reads in a vector 2, x and y, and does not use the z-axis. It doesn't need it. It's a good thing that that exists because the math to convert 2D space to 3D space can be very complex. Then, on line 39, we're using the Raycast method of the physics class. With the Raycast method, we are going to shoot a ray forward. We need to specify what ray we want, and in this case, the ray that we generated on line 37. We're going to pass in a variable called hit, which is of type Raycast hit, and the out keyword basically means that that hit variable will contain the data of any collision that happens. The next variable, 100f, specifies how far the raycast will shoot. If we don't have that value, then the raycast will go all the way to the edge of the camera, and that's very inefficient. We only really need to shoot out about 100 units. Finally, we have something called what is ground, which is a layer mask, a data type you're not familiar with yet. We'll look at this more later as we build the characters of our game, but for now it's worth knowing that what is ground specifically is a layer mask that allows us to choose the various layers in the inspector that we consider the ground for the purpose of this raycast. The rays will only be able to hit the things that are on those layers, selectively ignoring things that are not on those layers. So we don't have to worry about raycasting into, say, the player or buildings. We only want to raycast to the ground. Physics.raycast returns a boolean, true or false, and if it's true, we know we hit something. If it's false, we don't do anything. If we did hit something, however, we set the boolean flag is valid to true, and we say mouse position equals hit.point, which is the vector 3 location of wherever our mouse is in 3D space. That may seem confusing, but when we get to it in the project, we'll see it in action, and that should help clear it up a bit. Mostly I wanted to show you this block of code to show you the different raycasts and the more complex ways that we can use the simple concepts we've already seen. Really, all we're doing is we're using variables like vector 3s and vector 2s. We're using methods like raycast and screen point to ray, and we're using conditionals, an if statement specifically. All of these simple building blocks are coming together to build something that seems a lot more complex. The next interaction I wanted to identify was how attacking works. We're going to handle attacking in great detail in a later section, but for now I just wanted to identify this simple flow of logic, helping you to identify how we can move from one script to another script to another script to achieve a multi-tiered effect. This script here is the player input PC script. This is the script that will control the player's inputs and movements when we're on a PC platform, or more specifically, any platform that's not mobile. On line 66, we have a method handle attack input. The first thing we do is we say if player attack equals null, meaning nothing if we don't have a player attack, just return, leave this method. Next, we say if get button down, switch attack, which is an input axis that doesn't exist yet. That's one we'll be creating later as we start building the character's attacks. Then we're simply going to call the switch attack method of the player attack script. You should be familiar with line 76, if input.getButton fire 1. That means if we've touched a screen, if we've clicked with the mouse, or we've pressed the left control by default. If that happens, we're going to call the fire method of player attack. That's the one we're mostly interested in. So when we call the fire method of player attack, let's take a look at exactly what that does. In the player attack script, the fire method handles beginning attacking with whatever attack we have queued up. There are 4 attacks, but we are actually only handling 2 of those in this method. Some of our attacks only fire when we let go of the fire button, not when we first press it. In any case, we're going to look specifically at the lightning attack. We can see on line 58 and 59 that if we currently have the lightning attack queued up, we call the shoot lightning method. You might be curious about the structure we're using on line 56 through 64. This is called a switch statement and is effectively an if, else if statement. We simply say switch attack index, and then we say what do we do if that index is 0 or if it is 1. We use switches a few times throughout the project code. They're basically just streamlined syntax for if statements. The shoot lightning method begins on line 86, and the first thing we do is we say if we don't have a lightning attack, by saying if lightning attack equals null, then don't do anything, simply return. Then on line 91 we say lightning attack dot fire, again calling a method on even another script. In lightning attack we can see the fire method. Here we're generating a ray, very much like we saw in the mouse location script, only this time we're not trying to convert the mouse position to some 3D coordinates. Instead, we are simply saying transform.position, i.e. the position of the player. We're simply saying transform.position, meaning the position of the current player, and transform.forward. Transform.forward means along the positive z-axis. We treat the positive z-axis as the forward axis. Then on line 21, we're raycasting, very much like we saw in the mouse location script, using our ray, our out hit, our range, and our strikeable mask, this time using layers to determine which objects we can shoot. This time we're not looking to shoot the floor, we're looking to shoot enemies or any blocking obstacles like scenery. There's more stuff happening inside this script, but mostly I want to look at line 28, where we can see that we are creating a reference to an enemy health script named enemy health, and then we are using the getComponent method to get a reference to that enemy health by accessing the collider value of the hit variable we created above. Again, you can see how these basic principles, using getComponent, using if statements, using public methods, all come together to build a cascading, complex system. The last example I wanted to look at is in the enemy attack script, specifically the attack player coroutine. Whenever an enemy is generated, they start running this attack player coroutine. You can see the first thing we do inside the attack player coroutine is yield return null, which means wait a single frame. This is in case our enemy starts up before the rest of our game is ready to start. This prevents any errors and gets everything working smoothly. Then, we're looking for something called a game manager. We'll talk more about that in the chapter where we set up the player and allies. But basically, if we don't have a game manager, we're going to exit this coroutine by saying yield break. Then on line 57, we have a simple while loop. What we want to know is, can this enemy attack, and is the player currently alive? That code is stored inside our checkPlayerStatus method. Inside the while loop, if the player is in range and we're not currently slimed, because enemies can be slimed and thus not able to attack, then we are simply going to tell the game manager that we damaged the enemy. And then we will yield return an attack delay, which is some time in seconds that determines how quickly an enemy can attack. Again, we're seeing our simple principles, coroutines, yield return null, while loops, and simple wait for second delays, all coming together to allow our enemies to attack the player and make this game challenging.